Hi, everyone. My name is Jeff Wagner. I'm the technical lead at Open Force Field, and because of some audio troubles with the original recording, I'm redoing my recording of this demo. But basically, we'll see if we can splice it into the original video. Before this, OpenFold showed sort of a vanilla use case for how to take a protein sequence and turn it into a 3D structure of a protein and then do some relaxation with Amber. This demo is going to take the ending point of the OpenFold demo, show you how to take that predicted protein structure, superpose a ligand on it, and advance that to a physics-based simulation, which is suitable for the third demo in this series, and that is a suitable input for the third demo in our series, which is Open for Energy, showing how to use physics-based calculations in these larger workflows to calculate the predicted affinities of ligands binding to this protein. So I'll go ahead and do a bunch of importing gobbledygook. And the first thing that I'm going to do is I'm going to load the output from OpenFold with a superposed ligand into an open force field topology object. So this topology.fromPDB method takes in a PDB file containing the 20 canonical amino acids with the different protonation forms available, and it also recognizes caps. It also can load water and common salts like sodium and chloride. And if you have a small molecule, it can load that as well. But note that PDB files do not contain formal charge and bond order information. And so for things that aren't these canonical residues that you can look up in the chemical components dictionary from the CCD, if you're not that, then Open Force Field says, hey, you need to tell me the chemical identity of that molecule, including all the stuff like the bond orders and formal charges. Um, but as long as you have your ligand in there and it has connect records telling us where the bonds are, even though it doesn't have to tell us the order, and the formal charges, we can load arbitrary small molecules in complex with proteins or in the context of other atoms and residues in the PDB. So we can go ahead and take a look at this. We have our protein shown here as ribbon. This is not yet solvated. There's no ions. And we have our ligand superposed to be in the binding site. Let's just say we could have run autodoc vena, but here, because this is a canned example, I knew where it's supposed to go. Now we can solvate the topology. Using a quick workflow, we dump this out to disk. We call the OpenMM PDB fixer tool and say we want to add some water. This is a small box. You should probably use a bigger box. But and add sodium and chloride at a specified ionic strength. We can go ahead, load that back up with the exact same command as before. This time we don't have to specify the smiles. We just say the small molecule in here is that small molecule you've seen before. And we can take a look at the output. This periodic box is correct. It is just choosing to be based at the origin instead of the actual center of the box. A little bit annoying, but the physics of the system are correct. And we can see we've got these purple sodiums, we've got these green chlorides. And if we zoom way in between this forest of water, we have our small molecule ligand still bound to our protein. So now we'll go ahead and prepare a physics simulation of this, and I'm going to walk you through the basics of how Open Force Field does physics. And the first thing that I need to explain to you is how Open Force fields look. So this big text here is written in the language of smarts or smiles, and this is describing a chemical pattern where we will be applying a bond parameter between two atoms. So the atoms are these things in brackets, and we can read them from kind of left to right. This is element number 6, that's carbon, with 4 bonds, so an sp3 carbon. And this has a special tag value of 1 because it's in a bond. There will be an atom tag number 1 and an atom tag number 2, and that says where we're going to be doing the physics of this bond. The bond that we're going to be applying physics to in this case is a single bond. It's this little dash line instead of an equal sign that you'd see over here. And we're saying, so this is going to be our carbon, and it's going to be bound to element number 7, a nitrogen with 3 bonds, and that's atom number 2 in the bond. Further, this parameter says, hey, this is only going to apply in the context of a neighboring carbon with 3 bonds, so an sp2 carbon, double bound to an oxygen with 1 bond and no formal charge. So even though these aren't having their physics affected, like we're not describing the physics of bonds to these two atoms, it's still required for this parameter to be assigned between these two atoms that these two be here. And if these aren't here, then a more generic parameter from the force field will be used to provide the physics parameters for this bond. So what this looks like in practice is up here, we have two example molecules. And for each atom that's matching one of these tagged or like bracketed atoms in the smarts, we're coloring it with the appropriate color. And then wherever the bond matches, we're showing it in green. So the bond matches once over here. See, we've got the nitrogen on one side, that carbon on the other side, and we have this context of the carbonyl down here. And likewise, this is applying to this bond in a ring as well. Right over here is green. And it's a general force field. So it doesn't only apply to this molecule. It doesn't care about atom names. It only cares about elements, bond orders, formal charges, stuff like that. And so it can apply to other molecules pretty seamlessly, even if they look a bit different, like with the sulfur over here. And let's take a peek at what an entire force field looks like. So here is that parameter that we were just looking at. We like it because it's got non-capturing atoms, so it's a little bit instructive. But this is bond 9, or B9 in our force field, and it has associated length and K values for the actual physics of the bond that will be used in the simulation. And these all have units. I'm not going to belabor that. And yeah, this is what our force field looks like. It's just a giant list of these parameters. We can go down a bit. You'll see them start including halogens and lots of things describing hydrogens eventually. And one important detail of this is that the same bond can have different matches. So like at the top, we have some things that are laughably generic. So here's like any single bond between any two sp3 carbons. Like that's as generic as it gets. And there might be other scenarios. There's a lot of 6x4s, 6x3s up here at the beginning, and you look down and you start seeing 6x3s. If two parameters both match for a bond, it's the last match that wins. And so that makes it so that you can have this hierarchy of more generic parameters at the top for kind of broad regions of chemical space. But then if we start seeing deficiencies in our force field, we say, oh man, this carbon-carbon bond starts behaving really differently if one of the substituents is a halogen. Then we can make another parameter that's similar to it down below in the force field, and that lowest match in the force field will win when it actually comes to assigning parameters. If we go down below bonds, we see that there's angles. These angles have 3 tagged atoms, :1, :2, :3. And that's because they're describing the equilibrium angle between 3 atoms. And it really gets fun when you get into torsions because they have 4 tagged atoms. And in fact, they're a series of cosine terms, so they can get really complicated because there can be a bunch of cosines that get added up. So that's what our force field looks like. At an individual parameter level, all the parameters know where to apply because they have language like this. And then we just have lots and lots of them. And when we need to get more specific, we can just have later matches override earlier matches. So what does that mean in the context of how we're actually applying this? So here we're making a force field, and we are actually loading 2 files into a single force field. We're loading that file that I just showed you, OpenFF 220, or like Sage 220. And after that, we're loading FF14SB, which we've ported to Smirnov format. And what this means is that in every one of these sections, in the bond section and the angle section, it will first have all of the bonds from that generic force field that I just showed you, followed by all the bonds of the second force field. That's going to happen for all the parameter sections. And what this means is we have a single force field that when it sees protein chemistry in our topology, it's going to be assigning values that we've ported in from FF14SB. And but those will only apply to things that are complete amino acids. So if it's something like an amide bond, but it's not a complete amino acid, it's going to get it won't hit the specific terms in this force field. It will get the generic terms from this force field. And these force fields also contain all the charges for the molecules in the topology. OpenFF 220 has lookup tables for the charges in water. We use tip3p water. That's going to get better, but right now we use tip3p water just for compatibility. And we know the charges for ions, I mean just +1 and -1. And FF14SB has the partial charges for all of the protein residues. The one thing that we do kind of behind the curtain is we've called out for the small molecule, this ligand, we've called out to Antichamber from the Amber Tools suite to use their AM1BCC implementation to calculate charges for this small molecule. So that all happened behind the scenes. That's why this cell took 1 minute and 18 seconds. Most of it was going off behind the scenes and calculating partial charges using this open source stack. So we make our force field. We combine our force field with our topology, and we have that create an interchange. And an interchange is a representation of a simulatable system with all the physics that's ready to be exported to OpenMM, GROMACS, Amber, what have you. Here we're going to be doing an OpenMM simulation. So we put in some boilerplate simulation setup stuff, and we run 1,000 steps of an OpenMM simulation. And here's what that looks like. This is some fairly standard NGL view stuff to visualize the output of the simulation, but sure enough, it wiggles. We can see all the atoms in here, and they're moving a bit, and the ligands mostly staying put. Yeah, so in conclusion, in about 10 lines of OpenFF code and then a few lines of other people's code, we have loaded the output from OpenFold, and we've sent it to a physics simulation. Open force field in general can load these PDBs consisting of the 20 amino acids, waters, common salts, and user-defined small molecules. And so that means that after OpenFold has done this relaxation protocol where it makes a prediction, then it relaxes it in Amber, that's perfectly valid as input for open force field. I've shown you that open force field application is hierarchical, and so you can join together multiple force fields. You can make a force field more specific. We want people to open up the hood here and tinker. And finally, that, for other people who would be setting up a simulation in another ecosystem, you'd have some trouble assigning partial charges. And we don't. We use this fully open source backend that just happens behind the scene. The user doesn't have to think about it. And in fact, in the near future, we're expecting that this experience will get a lot better as we make our graph neural network chart assignment tool, NAGL, available to people. Since I've got some extra time, let me go ahead and show you a little more material. And the first thing that I want to show is this upcoming product that we're working on. It's kind of a late stage prototype now, and we're hoping to have it out before the end of the year. It's this tool called NAGL. And like I had said before, one of the big problems when we're setting up simulations is that for components of the chemical system where we don't have library charges prepared, we have to go and run these semi-empirical quantum calculations, and those scale very poorly with molecule size. These are AM1BCC semi-empirical calculations. The gold standard for kind of the implementation of these is in the OpenEye toolkits. They do AM1BCC ELF10, and that makes it less conformer dependent. But still, that requires a license, and using the open source backend is slow, and big molecules are basically impossible to put through. So we've made this graph neural network to assign AM1BCC charges. It's called NAGL, and I'll show you NAGL. Here's a small molecule drug, linezolid, and just taking a quick look, it's got a bunch of heteroatoms. We've got a fluorine in there, so NAGL can handle basically anything that our old backend could handle. But if I were to go run this, it would actually take about 51 seconds. And so I'm not going to do that in a live demo. Instead, I've saved it, and I'm just going to go ahead and load these, the Antichamber, like Amber Tools, calculated charges later. But here I'm using the NAGL toolkit wrapper to assign partial charges to linezolid, and it takes less than a second. So where the Amber Tools backend would have been 51 seconds, this one is less than 1 second. And this raises a question, is it accurate? So I'm going to go ahead and load up the output from running it with Amber tools, which I had done earlier, the output from running it with OpenEye, which I haven't shown here, but I did that earlier as well. And then I'll go ahead and show you the differences for these partial charges. Or this is OpenEye minus Naggle on the left and OpenEye minus Amber tools and our dkit on the right for these AM1 BCC calculated charges. So a perfect method would have basically no lines. So here we're marching across the atom, or marching across the molecule atom index 0 to atom index 40 something. And we're showing the difference between our reference implementation, OpenEye, and our graph neural net implementation, Naggle. Ideally, you'd have no bars, but it's better to, it's not bad if you have small bars. And that's kind of what we're seeing here. The difference between Naggle charges and OpenEye charges is in almost all cases less than 0.025 elementary charge units. In 2 cases, it seems to exceed that. But for the most part, the charges are quite close. In terms of is this significant, we've done a few experiments looking at how condensed phase properties change, and some of them are really sensitive to changes in partial charges, though it depends on exactly where. However, we've previously been offering our open source backend as an alternative to the OpenEye backend, and that's what we're comparing here, OpenEye versus Amber tools. And there we have several more molecules, or several more atoms in the molecule that are exceeding 0.025 in one direction or another. And so if these were acceptable differences before, then this is certainly a big improvement. And we fit our force fields using the OpenEye backend because that's good for our big training sets. We have to put a lot of molecules through. And having the faster OpenEye backend is what makes our force field training possible. So by releasing Naggle, which comes closer to OpenEye charges than Amber tools did, I think that all of our users will start getting better performance from our force fields because they're going to be using charges more like how the force field was trained. So I can also go ahead and take linezolid and add on 15 glycines to the side. This isn't anything biologically significant as far as I know, but it is a larger molecule where if linezolid would have taken 50 seconds for AM1 BCC calculations, and linezolid plus a bunch of additional stuff would take even longer. However, if I calculate charges for this using Naggle, we're still well under a second. I think just due to machine load being different, this is even faster than it was before. And finally, let me talk about interchange. So I had shown you in the previous example how if we wanted to assign parameters to a complex involving both a protein and ligand and water and some salts, I had to take these 2 force fields and put them together. I had to load into a single force field object both the SAGE 2.2.0 force field and the FF14SB protein force field. And you might be thinking, hey, why couldn't you just use one force field for the protein, one force field for everything else, and then stick them together at the end? And system combination is a complicated thing. To put together topologies, which in our parlance means just the chemistry of the molecules before it knows any physics, to put those together is no problem. This is a problem that's been solved with SDF files. You can just put a bunch of them in there. And you can, a lot of these files, you can almost concatenate them and literally wind up with a new file. For simulation files, for files containing the physics parameters, these are often tricky to combine because simulations have information like functional forms, they have non-bonded cutoffs, they have a lot of details that have to match up for a simulation, like for these simulations to be able to be put into the same box in a physically sensible way. So we could always put together topologies pretty easily, like the chemical topologies, but it would be hard to put together the physics representations. But this is something that now our interchange project has early support for. So here we make a ligand interchange, and that's where we use the SAGE force field, and we feed in just the ligand. And we can take the protein and the protein force field and make a protein interchange. We have to flip a switch saying that we're using an experimental feature. I think the switch will go away in a few months and this will just become mainstream. But until then, we have to label this experimental. And yeah, we can simply take one interchange, combine it with another, and wind up with a complex interchange. So here's sort of, oh, and we get a little warning because we're using an experimental feature. But again, that will go away soon. here's sort of the mind map for the different pathways that you can take. You can import stuff from different input types. So for example, here we just used the from Smirnov method twice. We did create interchange and create interchange, which is the same path as from Smirnov. But we can also load components from the Foyer materials modeling ecosystem. We can load anything that OpenMM can load. And so OpenMM has readers for a number of different file formats, and we haven't tested these extremely extensively. So go ahead and let us know how these work. But we can load native GROMACS files, and also we can make a new interchange by combining two previous interchanges. We can also write out to different formats. So we can go out to LAMPS, OpenMM, GROMACS, and Amber. And just to show you that it's sane, here we go. Here's that interchange that we just made by combining the already parameterized ligand and the already parameterized protein. But it's easy to go and draw atoms looking like they're in the right places. It's hard to get physics right. And so we've also made this sanity checking machinery in interchange, where we can say, hey, go ahead and take this protein ligand complex and evaluate its energy in a bunch of different engines. Not like have our own implementation of GROMACS's energy evaluations. I mean, no, write this to GROMACS and have GROMACS tell us what the energy is. And we've broken it out by components. So here, if we take that combined interchange, we send it out to OpenMM, we get these bond angle torsion electrostatics and van der Waals energies. And this is evaluated using OpenMM. Here, these amber energies are evaluated using Sander. These are evaluated using GROMACS and LAMPS. And we can see for the most part, things agree well. We have some slight differences in bond energies, I think, due to the use of hydrogen bond constraints. We have some very small errors in angles, but really not very much at all. You have to go 5 or 6 decimals in before you start seeing any differences in angles. Torsions are mostly the same. The LAMPS is doing something a little bit strange. And we see some slightly larger differences in electrostatics and van der Waals, but these are things that these warnings are telling us about. They're saying, hey, the Smirnov force field says to use switching, and some of these engines don't support switching, so we'll go ahead and do the evaluation. But maybe they don't do switching at all. Maybe they do switching in a different way. And so you can expect to see some differences. And that is what we see. It looks like we have to go to about the 5th digit, maybe the 4th digit in some cases to see these differences. And same with van der Waals. So I have just shown you that we can use Snaggle to quickly and accurately assign AM1BCC ELF charges. And this is undergoing final validation. There's a prototype you can use right now. It's exactly how I showed it in this notebook. Or we'll be making lots of announcements, shouting it from the rooftops when we make the full release. And also that interchange can do some pretty cool stuff for modeling workflows. And so it's gotten some new capabilities. You can refer back to this figure. And yeah, we're hoping that this will let people mix and match a bit in what they model and how they do it, using what force fields, using what engines. Because ultimately, I think we all win when we can do that. Well, and actually, seeing as I do have a little time left, I wanted to share something that bothered me a little bit. So when we were preparing to do this workshop, I was coordinating with the OpenFE and the OpenFold people, and we had agreed to use MCL1 as our protein. And so before OpenFold had sent over their predictions, I did a search on the protein databank for MCL1, and the first thing that came up was this PDB code for HW3 with this nice ligand in here. And so in the early parts of preparing my demo, I was looking at parameterizing this. But one thing I noticed when OpenFold sent over the prediction, and so I'm showing the OpenFold prediction here in gray with the surface, that's a protein, and then I'm showing the 4HW3 ligand. Well, the OpenFold prediction was made in the absence of a ligand. So it is, I believe, trying to model the apo form of the protein. And so if we take a look at this ligand, and I guess I'll turn around, we see that many parts of this ligand are actually poking through the surface of the protein. So the OpenFold prediction is modeled in this way that it has this cryptic pocket. where in the real world, a ligand will bind to this, but in the state that OpenFold had modeled the protein in, it would be a clash if you tried to put this ligand in. And so in the part above, I had only done this sort of external part of the ligand, this little ring system up here. So it got me thinking, using OpenFF, could I make a workflow to open up that pocket? By maybe iteratively mutating the ligand and seeing if it can push its way. We can do a minimization every time we change the ligand, and we can have it push away these protein side chains and see if we can turn the OpenFold prediction into a form of this protein with this cryptic pocket open. So here's a cycle that I'm imagining. First, we'll take the protein ligand complex as it currently is, and we'll relax it. And that way, if there's any clashes, we can resolve those before we propose mutations to the ligand. So this would say, look at all the carbon-hydrogen bonds, or look at all the kind of terminal bonds on the ligand as we have it currently, and try modifying those to methyls, try modifying those to amines or hydroxyls, and see if we can grow the ligand in a way such that it either makes more favorable contacts with this protein or extends the ligand down into this cryptic pocket so that the next round of minimization can open up the cryptic pocket a bit more. So once we've proposed these ligand mutation candidates, we will look at their geometry and we'll say, hey, is this growing towards that cryptic pocket that we want to open, or is this going out into the cytosol? And we'll only keep the mutation candidates that move the center of mass of ligand furthest in towards the pocket. And finally, we'll look at all of these and we will pick the mutation candidates that have the most favorable interaction energy with the protein. And so this is both to see if we can pick up a hydrogen bond on the way in, but also mostly, I think, to avoid clashing structures. So if we've added a methyl to the ligand, but that methyl is completely overlapping with a protein side chain, and we're going to attempt nuclear fusion, then that's bad. We want to introduce gentle clashes that we can relax out of, but we don't want to have clashes that are going to make our entire simulation explode. So working on this first part, I wanted to take a look at the ligand even as it was just in the original state. This is the scaffold that I was showing below and the OpenFold prediction. And we see that there's actually already some clashes here. The OpenFold prediction, again, is in the apo state. It didn't know that we were going to put a ligand here. And so the ligand, when I've superimposed it, I had to minimize it early on to remove this clash before I started the simulation. So this will be a good test bed for if we can get our minimization working. Now I'm going to introduce some boilerplate code here. This is all straight OpenMM stuff from the cookbook, and I won't go super deep into detail. These methods basically do what they sound like. Now, putting together the code to use OpenFF to relax the protein and ligand. Well, first, I'm going to kind of lay out my ingredients. And in this first cell, I'm putting together the force fields that I'll be using for the remainder of this demo. I'm going to make a Sage force field. I'm going to make a FF14SB force field, and this is analogous to what we had just done up above with interchange, where we parameterized the components separately and then combined the interchanges. And for clash resolution, I'm going to make this softened force field. And this is just going to be Sage, the same as we have up here. But I'm going to reduce all the van der Waals radii by half. And this is that force field that we're going to use to quickly evaluate the potential of these ligand mutation candidates and say, oh, is this introducing an unresolvable clash, or is this something that is either not introducing a clash or a clash that could be resolved with minimization? So we just use this half-scaled van der Waals radius force field for rapid evaluation of these mutation candidates. I'm also only going to parameterize the protein once. So I'm taking this protein interchange, making it once, and then in future steps, I'm only going to update the positions of this. And actually, the thing that I'm going to need is a protein simulation as well. This is a simulation of the protein without the ligand. And this is something I can, again, update the positions in and reuse. This one's going to be important for calculating the interaction energy, since that's going to be the complex energy minus the protein energy minus the ligand energy. But the chemical composition of the ligand is going to change every time. The coordinates of the protein are going to change every time. So by preparing a simulation now, I'm saving 2-3 seconds per iteration of this loop, where I can just update the protein simulation coordinates and rapidly evaluate the energy. Okay, now let's look at this method to relax a ligand in the presence of the protein. So here we're going to use that trick that I had shown above, where the protein has already been parameterized, so we can expect that to be passed into the method. For the ligand, we're going to use Nagel to assign charges, because again, we're going to be proposing a bunch of different ligands here. By the end of this demo, we'll have proposed 45 of them. And we don't want to wait for 45 AM1 BCC calculations, so I'm using Nagel to rapidly get the charges on these. For each complex, I'm doing the interchange.combine trick. And one thing that's cool, so we can do all this automagic stuff. Like there's so many lines of code that are running behind the scenes for all of this neural network stuff, and we don't want the user to have to worry about it. All this interchange stuff, very complicated. Not your business. But when you do want to open the hood, we make that really available. So here, in addition to creating this protein ligand system for simulation, we are going to go over to this OpenMM system that we've made, and we're going to say, and this is from experience, putting together this demo, I learned that a great way to resolve clashes is to simply push the protein and the ligand far away from each other. And so here we're putting in some spatial restraints. We're saying the original ligand atoms have to remain where they are. We're restraining them to their original coordinates in XYZ space, and same with the protein backbone. We'll let the protein side chains get pushed out of the way, but we can't resolve these clashes by simply having the ligand exit the protein binding pocket and then no longer having clashes. So here we've popped the hood. We're talking directly to OpenMM using OpenMM methods, and we can put that right in our loop. This is very fast. And then once we've introduced those restraints, we run a short minimization and simulation, and we save out the positions from this. So for every ligand candidate, we're not going to be restarting from the initial protein coordinates, because remember that the protein binding site is closed and we need it open. So for each time we're proposing a change to the ligand, we're having the protein adjust its side chains, open up its binding pocket a little bit, and then we're going to remember that conformation of the protein for the next iteration as we make further mutations to the ligand, so that we don't have to reminimize everything from the beginning, and we'll gradually open the protein binding pocket. We can go ahead and check that this worked by taking that, that clashy structure that I had shown you initially and double checking how it looks after we run this relaxed ligand routine on it. And sure enough, where up above we had seen several atoms with their whole bonds kind of sticking through the surface of the protein, here the ligand is almost entirely outside of the protein binding pocket. I'll go up to compare. But yeah, before we had entire atoms, entire bonds, parts of this ring sticking through. And now the clashes are almost entirely resolved. Okay, so there's our routine for relaxing the protein and the ligand. Next, we want to put together a routine to propose ligand mutation candidates. And like I said, we're going to try mutating all of the terminal atoms. We're going to try mutating them to methyls, to amines, and to hydroxyls. So here, these are RD-kit reactions, or these are smarts reactions that can be handled by RD-kit. And basically, we're saying, hey, for every terminal atom, try changing it to a methyl. For every carbon-hydrogen bond, try changing it into an amine and a hydroxyl. And one thing I want to highlight here is that OpenFF does not want you to modify open force field molecule objects. Don't add bonds, don't add atoms, it'll mess everything up. But we have a very high degree of interoperability with RDKit. And RDKit loves modifying your molecules. RDKit's great at reactions. It's got some of the best-in-class stuff in our field for performing chemical reactions. And so what we're doing in this part is we're starting with an open force field molecule, and then we're immediately sending it to RDKit. We've defined these reactions that we want to try. We're going to run all these reactions, and then we're going to do some boilerplate sanitization. And you'll see this in a lot of our demos involving RDKit. This is just to make sure that we don't have disagreements with the aromaticity model or other dirty things, and that we're copying metadata like residue name over to the new atoms, because we're going to need that to look at restraints and for other visualization things. So this is going to go ahead and propose a bunch of mutations to our ligand. And let's look at what those mutations look like. So the first reaction that we had in that list was converting all the carbon-hydrogen bonds to methyls. And sure enough, here's the original ligand scaffold, and we're proposing adding a methyl here. These are actually different structures. See, the chlorines are on bottom, the chlorines are on top here. So these are different positions where it's considering adding a methyl. And this is systematically going through and looking at adding a methyl onto all of these terminal atoms. The next reaction was changing carbon-hydrogen bonds to amines, and we see that we get that as well, and the same for hydroxyls. So these are all the candidates that were generated by our loop that we could try in our workflow. Now, for each of these candidates, we don't want to just build out the ligand randomly and have it going out into space. We only want to keep these mutation candidates that move the center of mass of a ligand towards our desired pocket. And so I took a glance at our PDB structure and I found the location of the pocket. It's at roughly coordinates 419. And this is in angstroms. And so for this objective function, where we say how close is the ligand center of mass to the pocket, I simply calculate the ligand center of mass. I measure its distance to the pocket, and I use a Pythagorean theorem, and I can run this on this whole list of mutations. Each one of these is the smiles of the mutated ligand, and then here's the center of mass distance to the pocket, and sort of helpful that this starts right at 10, because we see that some of these are dropping down to 9 point something, and these are the ones that are the promising mutation candidates. These are the ones that are moving directly towards that center of mass, or they're moving the ligand center of mass towards the desired binding pocket. So step 3, that was pretty easy. And now finally, this one's a little more involved. We want to pick the candidate with the most favorable interaction energy. And again, this is to help us potentially pick up a hydrogen bond, but mostly to help us avoid catastrophically bad clashes if we've added a methyl on top of a protein side chain or something. So to calculate the protein ligand interaction energy, we quickly assign the ligand parameters, and I'll note that here we're using that softened force field. So this is a one where the van der Waals radii are all multiplied by 1/2, and this is going to make it pick up the really bad clashes as terrible interaction energies, but only partial clashes, things that could be resolved with a minimization, those will be kind of forgiven by this force field and their energies won't be that bad. So for each one of the ligands, we assign it charges using Nagel. We make an interchange using that softened force field, and we get the ligand energy in vacuum. Then we get the complex energies by making a complex interchange. That's by reusing this protein interchange that we had made before, and we just keep updating its coordinates and combining that with the new ligand interchange that we had made. Then we can just calculate its energy real fast. And finally, this is sort of the clean conclusion, is we say the interaction energy is the energy of the complex minus the energy of the protein and the energy of the ligand. So if this is positive, that means that there's a clash or a bad interaction, but if the interaction energy is negative, that means it's a good mutation with favorable interaction energy. And now we make our final loop. In this loop, we keep track of all the candidates that we've evaluated. In this case, I'm kickstarting the loop by saying the initial ligand is 999 angstroms away, but it's your only choice. So this will be selected for the first iteration of the loop. But then everything else is going to be around that 10 angstroms that we had looked at before. We're going to use that routine I had shown before to relax a candidate. And because this whole workflow is big on introducing steric clashes and hoping that we'll get out of them, we can catch errors where OpenMM just throws its hands up and says, I can't possibly resolve this. So if there's an error, we'll just go ahead and try the next candidate. We're keeping track of some of the data as we go through these steps, but we'll get the protein energy, we'll propose these mutations, and we will reuse that protein energy here for each candidate. For each candidate mutation, we're going to go ahead and calculate its interaction energy, but we're going to reuse that protein energy each time. And then we'll print out a little summary of the step, sort the candidates by who's getting closest to that center of mass, or who's getting the ligand center of mass closest to our desired pocket coordinate, and then repeat. So I ran this ahead of time. It does take a little while. There's some, most of the time is actually in exporting this system from an interchange to OpenMM, and this is a performance thing that we're working on. There's no reason it needs to be that slow, but for the most part, creating the OpenMM simulations, assigning charges, proposing mutations is all lickety-split. And we can follow this through its rounds. So through the first round of mutations, it's proposing these different ones, and we're seeing that most of the interaction energies are quite good. They're still negative, meaning that we haven't introduced any terrible clashes. In the second round, we do start introducing some bad clashes, so this one's not going to get picked. Probably this one with a negative 106 kJ per mole. And as we move through, it kind of gets a little bit harrowing. The interaction energies all become positive. They get up into the thousands. We're heading up in the tens of thousands. But it seems like after running into the protein, it does, well, it gets to a few moments of tension, but eventually it relaxes a bit and it manages to clear up whatever conflicts it's having with side chains. And some of the final interaction energies are no longer magnificently positive. They're coming back towards zero, still indicating a tight fit, but we're not allowing much in the way of minimization. So the fact that it's able to resolve these at all is great. So this has performed 15 actually successive mutations in order to bring the ligand center of mass closest to this cryptic pocket that we want to get it towards. And let's take a look at what that actually looked like. Okay, so here's that initial configuration that I had shown you before. And if we step through, we see it is indeed building down into that deep pocket. Let me run this once more. Maybe I'll come from this side. But it's picking mutations that move it in the direction of the pocket. And we see the surface of the protein, whoops. The surface of the protein is indeed changing. So this surface drawing, while it's initially closed down here, each mutation is indicating that after relaxation, the protein did have room to open up. So that's pretty nifty. And I think one important thing is this too good to be true? Did this open up a completely different pocket from that initial structure that I had found with the buried ligand? And we can compare the final frame of this workflow to that 4HW3 protein that I had found before. And looking at the two surfaces, it does look like our workflow here basically followed the same path. We see the two ligands overlapping well. Both of them mostly fit within this binding pocket that we forced open. And so it looks like this workflow did work. Now, this is you can check the scroll bar on the right. This is the real end of my demo. I think the big thing I wanted to point out is that the initial scope of this demo was to show you how to go from an open fold prediction to open free energy, an open free energy compatible input. That is very easy. That takes 10 lines of open force field code. And all the rest of this was showing you some of the upcoming exciting stuff that we have coming out with Naggle, with Interchange. We've got a bunch of other tools in the oven that we're working on getting to you. And just how easily you can put together a workflow using these tools and how it can be, kind of performant and highly customizable. Anyway, with that, I'll wrap up and turn it over to Open Free Energy.